I'm Trevor Grant. I'm a PMC on Apache Mahout, a PMC on Apache Streams, open source evangelist for IBM, and data scientist is a term that is abused and isn't really cool anymore. So I'm testing AI engineer is a sexy new thing. So let me know what you think. If you give me a 20, if you double my current salary with that title. So yeah, please also tweet at me or visit my website.
I'm Cote. I work for Lucidworks. I'm a engineer on the core team for Fusion, and I run a user group in Dallas called DFW Data Science, and that's in fact how I met Trevor and various other members of the open source community, which I'm a major fan of, and big fan of Solr and all things about machine learning. So, but I do not call myself a data scientist. There you go.
All right, Act 1, the math. So, how many people have heard of deep learning and think it's a thing? We're going to give you a very introductory overview into deep learning. Just kidding, no we're not. It's very fashionable, I understand that. And we're going to be very contrarian in this talk, and that we are going to not use deep learning for very specific reasons, and we're going to talk about that. I am going to go, yeah, who's interested in deep learning? I kind of got carried away this morning with memes. I want to put out there that I don't really hate deep learning that much. I've implemented it in a couple of machine learning libraries. I think it is, first of all, a marketing ploy that is grossly abused. People throw it at problems that it doesn't belong at because it's some sort of deep magic. That's what they mean. They mean deep magic that's going to somehow reverse years of mismanagement of their company, and they're all of a sudden going to be profitable because they use deep learning. And that's not really what it's for. One of the problems with deep learning is it's slow, it's expensive. Man, I went nuts with these GPUs this morning, or these memes. And one of the few cases where deep learning is the right thing to use is image detection and image processing and non-structured data. And so what if I told you you don't even need it there, that there's other approaches? And the two approaches we're going to talk about are cascade filtering and eigenfaces. And the big reasons we're looking at those are speed of training. First of all, now, not that we really care, but it's important. Deep neural networks, deep learning takes months to train. If you have GPUs and are willing to spend a lot of money, maybe you can train them up a little faster. The prediction, even when you're predicting records, and what I mean by that is, okay, you've trained your neural networks and you get a new picture in and you want to predict what are the faces or where are the faces or who are the people. That's still not fast. You've got several layers to go through and all these connections, and yeah, for batches, it's pretty quick, but when you're doing real-time video and you're taking frames in at 60 frames a second, it's still very expensive. You're still causing latency. And then I don't know, I kind of get snarky and say some other mean things. You can follow me up later. And this is what I always laugh at, is the deep learning mindset. If you've all seen the data science is hard XCDC, that you just throw a bunch of data into some deep learning and stir it around until the answers start looking right. Yeah. So fast prediction is relative. I kind of talked about this already. But again, on 60 frames a second or at high-speed video, even the prediction that machine like deep learning is doing, it's expensive. And I want to say in deep learning's defense that deep learning is going to be a lot more accurate. You're going to get better facial detections on each run, but we want to go fast, and we understand that we're going to have some misses, and we understand we're not going to be getting the best per frame image recognition, but latency kills slowly, and that's what we want to avoid. Milliseconds we can't afford. So, man, I kind of really belabor this point. I'm going to skip through. Fast, right, or cheap. Hard cascade filters. They're fast, they're cheap. And so if you're not familiar with the hard cascades, the general idea is going to sound a lot like a convolutional net, and that we look at dark and light areas of the picture, and we look for patterns. Fun fact on human faces, if we grayscale them, you normally get, if you look at the light and the dark patterns, you normally get patterns like the edges. You normally see patterns like dark spots of the eyes with a light spot in the middle. And it's patterns like these that the Cascade filter uses to detect a face. The EIGENFACES method, so we detect the faces in the frame with a Cascade filter. EIGENFACES, I don't know, I think that slide got moved. Anyway, is how we recognize who we're looking at. Now, if you think of a face, any face we can grayscale, and it's just a bunch of pixels. It's a bunch of grayscale pixels. And a grayscale pixels is really just a matrix of numbers. And we can take those numbers and we can turn them into a vector. Take a square. So we can represent any image as a vector. Now, we can take a lot of images and we can stack them up row-wise, and we can create a matrix of images. Columns represent a pixel position, rows represent the image, and we can do a singular value decomposition. And if you're not familiar or don't remember singular value decompositions, the gist is what we're going to get is these eigenvectors, which are eigenfaces. And if we took those eigenvectors and constructed them back into images in the same way we took them apart, they look something like this. And the idea is then the U of that singular value decomposition is going to be the linear combinations of the faces. And so the exciting part here, though, is if we had like 130 eigenvectors, we can represent images with vectors of length 130 instead of like a 250 by 250 image is like 62,500 pixels. So we've done a principal component, a PCA on facial images. We get new faces in, we take the new face as a vector, we can do like a linear regression and decompose it as, that's how we can break down new faces into combinations of these eigenvectors. So the point being there is these are both a lot faster than we could have done before, and we're not using neural networks. The other upshot of the eigenfaces, well, there's a couple others, but when we get new faces, all we have to do is add new vectors into our collection, so it scales a lot more linearly. All right, so that's all the math we got to hit. It's a lot easier than having to sit through neural networks, yeah? So that is that. Okay, I can take a breath and slow down a little bit. Actually, I'm going. We got a lot of slides, and I want to make sure to cover them all. But so because I've just gone really, really fast, can I get like some head nods? Does that all make sense? Okay, my clever use of images and things flying around, they paid off. All right. Now let's get into the fun part. So we're creating the eigenfaces. The way this gets done is we use Apache Spark. We use Apache Mahout on top of Apache Spark. Apache Mahout you might have heard of as an old, because Lucene and Solr have an old history. Mahout's done its old thing. It is now a library that runs on top of Flink, on top of Spark. So we can run Mahout on top of Spark. Spark has matrix decompositions, but they're not truly distributed. Mahout gives us a truly distributed. So that's how we train our eigenfaces. Train, and by that meaning we do a singular value decomposition on a large RDD of faces. And so we've created our face data set. Now, the faces in the wild data set is commonly available. I'm going through this kind of slowly because this code is all available. Anybody who wants to do this at home, GitHub account's there. If you've got some cool ideas, you want to jump in, contribute, and kind of, it's sort of just a hobbyist fun thing we're doing, but it's kind of cool at that. But at any rate, so faces in the wild, we do our decomposition, we get our eigenfaces. Now we're using a library called OpenCV, Open Computer Vision. That's what has our Cascade filters. An image comes in, it's really coming in as like an RSTP stream of video, but we're scanning. It picks up the images, scales the image to 250 by 250 because that's what our input images were trained on. Mahout decomposes the face into a linear combination of the eigenvector, or the linear combination, sort of like I was just talking about. Fun animation. Zoom. Okay, So now we've got this betas, or we have our combination, a vector length 130 that represents this face. We run it into Solr, and we get a response. We search Solr for that vector length 130. Now, because it's Solr, let's dive into that a little deeper. The documents we have in Solr, and again, this is a very first pass and not the most elegant use of Solr. We've got a name, and we have it a length 130 vector. We have 130 fields, each with the value. Maybe some other information, and that's it. And so when we're doing our search, our query, it is, oh, well, this is fun too. I didn't do it just the straight select query. It seems like there's not a lot of people using Scala in Solr, but there is Solr for J. But this is how, if anybody's looking at home and wants to do it in Scala, this is what it looks like. But really what we're doing is we're just doing a distance function of the numbers of the vectors we pulled in, and we're just doing a distance function. It's Euclidean distance, and then we're sorting by who's the closest. Makes sense. It's pretty intuitive. It's the way you would think to do. If you've got a bunch of vectors, you want to find the closest one. We're searching for it. Actually, I'm kind of out of my element here. Scott knows all this more than I do. So, but this is the kind of the cheap novice way to attack that. We get a response. Yeah. Oh, wait, no, your part's coming up later. Sorry, no, never mind. Yep. So then we have to decide, do we recognize a new entity? And the idea there is, okay, we have a bunch of responses. Do we recognize them? Are they close enough distance-wise to people we already recognize? If yes, then we say, okay, this is that person. If no, add this person to the database and move on with your life. And this is the, you can move all of this stuff locally, or you can do it on the Solr. And you can move it to the edge, or you can move it to the database. And this is a classic problem when you're doing this kind of AI, IoT stuff, is who does the work? And it depends. Where's your biggest bottleneck? Where's the cost? Is it the network traffic? Is it going to be, I mean, you could, in theory, just stream the images all the way back to some sort of server. But if that's going to cause a bottleneck in network traffic, then you try to push compute out to the edge. How much compute power does your edge device have? Do you have a full Raspberry Pi? Those are pretty strong. Do you have a very tiny little like thermostat which has no brains? The point here is it's the thing that you have to think of when you start doing this kind of AI and vision sort of stuff is where are you doing your compute? Right. It's just the call out there. So there's advantages to each. So then that gets into, all right, building our own Cylons. And this is a significantly more fun and I think an exciting part. We decided to do this on some drones. They sell these little guys on Amazon. They're very cheap because this is the world we're coming into. But for about 50 bucks for a drone and about another 30 bucks for a little camera. One of his wings is broke off, but you can get these little guys. They're fun, they fly around. They're very programmable. They sell little kits that you can use Adrenos to program them. It's a lot of little fun stuff. Now, these guys have like no compute power on them. And there's a few challenges. So that was the basic system that I kind of just walked you through. And a good thing about putting this in a real thing is you instantly start to feel the pain points. Like, okay, on paper, this all seems like it's going to work out just great. Where does it break down? Where does it stop? Cascade filters, first of all, inconsistently frame your face. If you've got a face, if you're doing video images, it will say, okay, here's your face, here's your face, here's your face, it just kind of bounces around. That makes it very hard for the eigenface. It also will pick up shadow. Oh, I can't look down and talk. It'll pick up shadows and other patterns, and it'll say, oh, that's kind of close to a face. And that's what I was talking about. These are the sort of things that your deep learning neural nets not going to be so easily fooled. Stupid cascade filters, yeah, it in a very minimal number of operations will detect a face, but it's easily tricked. It's the cheap, simple algorithm. So it changes in light. There's issues like that. We saved ourselves so much time and trouble because we wanted low latency, but now we have to pay the piper now. So The opportunity is we're not looking at still images. We're looking at video. And video gives us context clues. For instance, if this video right now is being taken of me, and if you were watching it, yeah, I walk around like this, I walk around like that. But what I don't do is stop existing here and start existing down there. Or some other person exists here for a half a second and then disappears. We have context clues that geometrically, our humans' faces tend to stay in about the same place or not drift too far frame by frame. We can use that. We also have, if we are doing a facial recognition like an AI kind of thing, you've seen me recently. Now, if for just a hair or a couple hairs of a second, I look like Abraham Lincoln, you still intuitively know I'm not Abraham. I didn't magically turn into Abraham Lincoln. That was just a couple of seconds. I'm still probably me. And so these are things that we can use. It's things that we as humans take for granted as we process video in the world around us, that when you start trying to do AI and this computer vision stuff, you have to think like, how do I know that Abraham Lincoln wasn't there for a couple of seconds? And you have to kind of encode it, but it's fun. So, like before, we have OpenCV, detects a video in a frame, but it's a video, so it's detecting and detecting and detecting, and it catches a ghost image, and so these are the frames that it picked up. Now, keeping in mind, this is kind of a not great animation because in real life, this was like a video. This was a simulated video, but over a course of 6 frames of a video, these are the facial rectangles I picked up. The face is inconsistently detected, which gives EIGENFACES a hard time, and we get these ghost images because of shadows and patterns. Now, one of the solutions we had was clustering. Simple clustering, and we're clustering on XY coordinates. The Euclidean coordinates, because as I was saying, your face stays pretty much the same place in a frame. And we say if we have a bunch of facial rectangles from this general area, that's probably the same person. And if we have like a rectangle that pops up over here or up here, but it's only there for a frame or two, that's probably a ghost. So let's filter out those sparsely occurring rectangles. And that was our kind of idea behind it. So we use something called canopy clustering. And there's a good chance you have or have not heard, or you haven't heard of this because it's not k-means. It kind of fell out of fashion. Its main advantage, it's not, once again, the most accurate. It's not great like k-means, but it can cluster the entire data set in one pass. It was originally used a lot on huge, ultra-large data sets, but people kind of got better at k-means, and we got, Spark and in-memory, and it's not quite as expensive to iterate. But we're still living in a world of, it doesn't have to be perfect, but we want to go quick. So as we get frames in, we can, we're not have to cycle over them. We're not burning cycles. So in this example, we've got, the way this works is the first frame it sees, the first face it sees is a center. And instead of trying to find the perfect center of the cluster, it says, all right, first face I see, you're a center. Now, until I see another face that's more than a certain threshold distance away, I'm calling you the center of the cluster. And then, yeah, and so that's how this works. Okay, animation. So these are all the rectangles the face rectangles. Got, this one's a center. Okay, cool. That's the threshold distance. Next one, in threshold distance. Next one, in threshold distance. Oh, that's not in threshold distance, new cluster. Okay, that's how the canopy clustering works. A little more to it, but that's good enough for a talk that's not on canopy clustering. Now, at the end then, we filtered out because there was only one rectangle down where the shadows were. So that's how we get rid of those ghost faces. Okay, so the reason we want to have this clustering is because in any given frame, we have somewhere between 0 and n faces, and we never know how many we're going to have. And so we have a long distance and a short distance, if you're more familiar with this algorithm. And the way we do that, our clever trick, is of all the rectangles that we've seen over, let's say, the last 5 seconds, the largest rectangle, the width of the largest rectangle, they're actually squares, is our long distance, and our short distance is the width of the smallest rectangle. And that gets into how we save ourselves from, because faces in the back, you'll see, are smaller if you're further away, and you can end up with people close together a long way away. When you have somebody up close, they get merged together into one person, things get weird. The point and the kind of the punchline here, if you're interested to get into canopy clustering, it's not super difficult. Spend like a half hour, just kind of read up like a wiki on it. But the exciting thing here is we have a machine learning algorithm that's adapting to its environment in real time. And that feels a lot more like real artificial intelligence than, oh, it's like data science, except a cool new word. So that's, if you ever wanted to think of like, okay, how do hyperparameters adapt in real time? There's a really easy but intuitive and example that you can follow along at. Another problem we had was I very admittedly came up with a naive and stupid way of indexing things into Solr. So that's where I want to hand over to Scott, because he did some really awesome stuff on that.
Yeah, we'll click.
Okay.
So we're looking at how the initial thing was going in. When the documents come in, we're doing a full scan every time. So with a small number of faces, this is not a big deal. I mean, Solr on a CPU can process lots of comparisons with the distance function just fine. It'll be okay. But as you start scaling up to larger and larger data sets that we all know Solr can handle, sometimes up in the petabyte range, this is not a functional process. This is a seizing up of the machine and looking at a smoking data center. So how do we get better? So the first thing we can do is we can change the query around so that the data is stored in a more compact form. So first of all, Trevor, when he put it together, he had individual fields explained out for each component of the eigenvector. So you see the E0D, E01D, E2D, E3D. There's a field for each and every single component of the eigenvector, or element, depending on how you want to talk about it. So let's go to the next one. So what are we going to do? So let's, instead of doing that, let's make one field to hold the whole thing and leverage the good work of Eric Hatcher with Solr 1485 of doing payloads. So what does that do? That allows us to stick everything in one field and have the magnitude for the elements associated with the terms. So you see under Richard Hatch, we have E_DPF, which is the endpoint you put for decimal payload, for the document payload with floats. So I have E0, 1.512, space E1, pipe 1.512, on and on and on. So this allows us to put the individual elements inside one field. There's many, many benefits we arrive from just doing this. So now we have a much simpler document. If we get to, say, 1,000 eigenfaces as opposed to 130, which we have now, this becomes really hard to eyeball, right? So all the other, as humans, we're not going to be able to read the document and see all the other attributes, because you're not going to care about feature E5 or E7. You just know that it's an element. I mean, you're probably doing something really weird if you're looking at those individual elements. But you care about the call sign, and you're going to care about the alias. So let's not drown those out in the design. Let's go on to the next. Oh, wait, go back to the query. The other thing we're going to do is in the work that was the initial approach was we were calculating the distance outside of Solr. So Solr has a nice functional query capability that was introduced in recent versions of Solr. And so we're going to calculate the distance between the query vector and the vectors in the documents. So I'm going to hit the payload for each and every, you can see that in there, the payload for each and every element of the eigenface vector. And we're going to do ascending, and we're going to say, give me the top 5. Now, this is still doing a full scan against the whole collection. So again, if we got petabytes of faces, this is a smoking crater of a data center. But at least we took the distance function out from outside the VM of Solr and put it inside the VM. So we're saving a little bit of compute time. Let's go to the next one. So again, we're scanning the whole collection. That's what this is about. We're scanning every face for every query that comes in. Not a good deal. Let's go. So what do? Let's use clustering again. So we're going to take all those eigenface vectors, and we're going to run a canopy cluster, maybe a hierarchical cluster on it. And then, instead of scanning all the faces below, we're just going to scan the vectors that represent the cluster geocenters. So the face comes in, it's going to scan the cluster top points and finds, better to match cluster 1, and then we scan the elements, the vectors that are associated with cluster 1. So this will reduce your scan time quite dramatically. The better your clustering is, the better it'll be. So that takes a little bit of novelty. You have to do some agility with your data. Again, the structure of the document plays out very nicely for that because all your fields that represented the elements are now jammed into one field. So if you want to make a new eigenvector thing, right, we have 130 right now, let's go to 1,000. Okay, well, we just make a new field for that. And you've got the originals data, and now you got the new data in the same field. So there's that, and I don't know. What else can I talk about with that? So, there's other things in the pipeline. There's a capability that's coming in Solr. There's a JIRA out there for instead of doing the payloads like you see me doing explicitly there. There's something there's coming. I don't remember. Forgive me not remembering the Solr JIRA, but it allows us to do custom term frequencies. So you can, instead of doing the payload, you hit the custom term frequency to do the comparison of the vectors. There's also in Lucene the capability, and in Solr, to do searches using the distance function with, say, latitude and longitude. But it tops out. Steve Rowe did a pull request for Lucene with, I think, 120 dimensions. But I don't know if it'll ever merge into Lucene, much less Solr. So this is the best we can do for now until Solr is better able to support multi-dimensional searches of this nature. We can't do the typical Solr search with specific terms and omitting terms and so on because this is a compact data set. Every feature counts. So it's a full thing. So it's in that way it doesn't make use of Solr in the traditional sense. So that's how you use Solr with this, and it becomes very fast, but you've got all the benefits of all the metadata about Apollo, and you can combine all those other things into the same facial recognition search. And that's it.
No, sorry.
Go ahead.
We got a whole other act.
Yeah.
So if we're thinking of all this, and I am definitely going out of my way to frame it as such. There we go. If we're thinking about this as an artificial intelligence type of thing, and Solr is the memory, then we need something to be our stream of consciousness. Like, how are we actually processing this coming in? For some reasons I'll get into in a bit, Apache Flink is an amazing, perfect, it fits the bill for a number of reasons. It is a stream processing engine. It has concepts of records coming in, has window functions. So we can have, this concept of like, all right, everything that happened in the last 10 seconds, everything that happened in the last 100 frames. And it's very dynamic in how it will let us window the information coming in. So the idea of another way to look at all of this, videos coming in, we are setting our canopies, we're applying the canopies, the clusters, to new frames as they come in, which is coming through. We're using Solr, we're hitting Solr to figure out our facial memory. Do I know this person or not? And then down here, we're taking the original frames and then merging it all together and giving ourselves a video out. Other outputs might be having the drone do something, alerting us that there's bank robbers, attack the humans, whatever it is. So to kind of illustrate this a little more, as you recall from the last slide, we've had these 5 frames or faces that we detected in the last however long. So we go through our canopy clustering, which we can set we can do a lot of different windowings and determine how long we want our stream of conscious, our short-term memory to be. And we do introduce a small lag here because we have, we're going to have to, even if we're only emitting things every like 1 second, it takes like a second to kind of keep getting it's a price we're going to have to pay slightly. But we can at least tune it and we can control for it. So this is where we realize, hey, that picture of his camera, that's not a face. let's drop that. And all the rest of the pictures are all from the same face cluster, even though they're different cuts and they look all different. Now, so once we have all these, we have to figure out how are we going to look at all these different pictures and put them into memory. I didn't realize I'd done this, but I was having a regression or a bug I was chasing. Apparently, my first crack was to take them and average them all together, and surprise, surprise, that gave me garbage and nothing useful. So if you were thinking maybe that's a good thing to do, it's not. It searched Solr for the average image. It would add it. It was very unstable. I was constantly having new faces be introduced. That is an unwise approach. But in the nature of science, you know, we even have to report things that don't work so others don't follow our mistakes, and that is a mistake. So other ideas would be to voting. We've got these 4 or 5 faces. Now this is going to cost more because we're going to have to be searching. We can search Solr for each face, and we get our responses, and we say, okay, what are the top 10 responses for each face? Now the problem with this is we're hitting Solr a lot hard. The upshot of the old method is we only hit Solr once every second. It's very, very light. Now we're hitting Solr 100 times a second. There's probably there's a happy middle ground. It depends what you're doing. It kind of goes back to that idea of, you know, where are you having where do you want the compute to happen? Where is it going to cost you the most? The upshot is, though, okay, on these 10 faces, I've got a different name for each person that comes back, but you'll probably have a couple similar names, and you can do some sort of voting schema that will do that. But the upshot here is that unlike a deep learning network, and this is one of the bigger critiques, though you can kind of hack and get around this problem, a deep learning network is going to be able to that's been longly trained, do a great job on 100 or 1,000 people, given all the pictures. It's going to pick out the right person every time until you add a new person. And then it's never been trained on that new person. It has no idea what to do. So how do you do that? Whereas on an EIGENFACES approach, you can have new faces coming in every second, every 2 seconds, and you can grow your database very, very, very fast. So it also, once again, depends on what's your application, what are you trying to do? But in a world where you are going to have lots of new people coming in all the time and you can't do deep, heavy retrains every minute, this is the thing that you want to look into. Why Solr?
Why Solr? Well, Solr, you know, it's, I have to be very impressed. I used to be an Oracle database administrator. I'll say that out loud. You know, it's a very expensive box. It's a lot of data in there, right? It can hold a lot of stuff, but you know, how much can you actually put in one of those monolithic databases? Solr is one of these databases that just grows and grows and grows and grows and grows. Very impressive capability to store data, and we're going to add lots and lots of faces. Well, let's just keep growing that database out. Let's take advantage of sharding, et cetera. So the NoSQL capability of Solr allows us to iterate over a variety of experiments. So, you know, the first time you do your cluster, you're going to pick 130. Did that work? You're going to pick eigenfaces of 130. Did that work out? Well, let's do it again, say 500 faces or 1,000 faces. What kind of clustering did you choose? What was your K? How did the canopy? What was your tuning parameters? All these different things. You're going to want to reiterate, iterate, and see if you're getting better and better and better. But you don't want to lose the data you ran before. So again, NoSQL plays very well into that. And Solr is very good for that. Solr is awesome with numeric computes and text analytics. Again, I come back to, okay, we're searching on finding the best face. But let's look for other attributes to incorporate in finding the matching face. Maybe we have other metadata like shadowing, or maybe the machine knew that we're looking at the back of the head, or you know, we're some geolocation. All those capabilities of Solr, it's all there to compensate and augment what's already in there with the eigenface. So many ways to store so much data. So this is why I've recommended to use Solr as the storage as opposed to using, say, a Hadoop, or say a Cassandra, or a Mongo database, which they all have these similar capabilities, but they all have inherent weaknesses. So that's why I think Solr is the best for this. So.
We had a couple other things. Apache Mahout. Why Mahout? A lot of people here might not have heard about Mahout for a long time or thought much of it. It's changed a lot, though quietly. Engine agnostic, runs on Spark, runs on Flink, runs on a couple others, runs standalone. You can roll your own engine. So if you got some crazy database and you really want to use Mahout, all you have to do is implement the abstraction layer. The in-core matrices and vectors have BLAST accelerators, which can be changed at runtime by swapping a dependency. So we can run GPUs, CUDAs, CPUs, or just standard JVM. Or, and what's very important if we're doing some sort of IoT situation, whatever weirdo little architecture you have on your edge device, not fun, but you can implement the optimization, and again, there's an abstraction layer, and then swap out a dependency at runtime, and then with the same code compile for JVM or compile accelerated at that edge device, et cetera, et cetera. And the real kicker, though, is it gives us mathematically expressive Scala. And so we can express whatever algorithms we're trying to put down, and we can do it in a few lines of expressive Scala. It's easy to see what we did. It looks kind of like R. It's very nice. Apache Flink we use because sophisticated windowing functions. If you're not familiar with Flink, it's a great project. If you're getting into streaming, I'm a big fan. I guess I don't have to say that a lot. Yeah, very sophisticated windowing, complex event processing libraries, and it scales linearly. So it's a true streaming engine, not like Spark streaming. We're not micro-batching. We can take events as they come in. And because it's a distributed streaming engine, I've been comparing this to Cylons a lot because that's what the little guys remind me of. But if we're going to be sci-fi dorks and extremely careful about how we speak, this is actually closer to Borg AI, and that there is a hive mind where all this is happening, and that hive mind is being Solr, as well as the streaming engine and like the central. To give you an idea then, one drone says, oh, this is a new human, stores the information, off it goes, doo-doo-doo. His buddy comes by, sees, oh, who's that? And without having to do too much, it's like,
that might improve on it.
That's the human.
Right?
What's up?
Might have new images that improve on it.
Exactly, and that's what it would also be then, as it collects new images of human 0001, it will add to the canon and say, oh, these are more pictures. So as you build these richer and richer profiles of that person, they become easier to identify as another idea behind this as well. Yeah, so this is this is where I start getting all philosophical. What was science fiction 10 years ago is now, this is a street vendor I saw. I was in Berlin giving a similar talk about earlier this week. This is in a park. This guy just built this robot dances. Does a very nice job too. It's a pre-programmed thing that it runs through, but it wouldn't take much to hook whatever's controlling its program up to something like this. It doesn't have legs, but it's got some sick dance moves and ability to throw. And that's wild. You could have that robot controlled with AI with probably a weekend project worth of a couple of hobbyists just jamming out. So that's exciting. The thing that I'm showing we're showing in general, this code, this is the science fair project of 20 years from now. The little kids in like 6th grade do to build some AI. And there was recently, old Vlad Putin said, it's undesirable for anyone to monopolize this new space. And I agree, not just nation states, but companies and whoever else, which is a great reason that all of these awesome components exist in the Apache Software Foundation. I'm really excited about that. And again, if anybody's interested in just kind of keeping playing with this, we're gonna get kind of a feel for how many people are into it, but we are definitely interested in continuing this project of just kind of toying and building AIs and like running into problems, coming up with the solutions, and then broadcasting the solutions so everyone benefits from it. Companies and nations, they benefit too, but when you've got some of the best in class AI sitting in open source, it's real hard for anyone to get a real competitive leg up. So that's kind of my shtick.
Democratization.
Democratization, I like democratization of AI. Right. We ran the entire thing. I'm glad I talked fast at the beginning. But we're happy to take questions after. We are at the end, right? Or do we have another 10? Who's running this show? We have 10 minutes still? I thought we were shooting for 40. Right. Okay, we got 10 minutes. We have a demo too that we'll do in the hall, but I don't want to videotape it yet because the network's unstable. Question?
So the Mahout project
Sure.
is not dead?
It's Mahout. There's a very
Very much alive.
I was recently interviewed in the title of the article. You can search "Mahout is not dead."
It's a redo.
Is text still accurate, or
On,
containing text is not the Mahout of today?
It is not the Mahout of today. We need to incentivize Grant to write a new one.
it's yeah, it was. We've deprecated MapReduce, and it's been deprecated for about 2 years since 0.10. I think we're trying to push 13.1 out the door. Now, yeah. Which, oh, it is 40. Okay. Well, good. Well, I'm going to keep standing on my soapbox till they kick me off the stage. It has changed a lot. I'm a PMC, so it's I'm really big into it. But it is, yeah, it's shifted to very ultra modular. It can run on any engine, any architecture, any. There are instances of it.
It's an expression language now.
And it's expression. We're hoping to maybe, it's right now in Scala. We're hoping to write some Python layers to it too. So pretty much every single piece of it can be swapped out. As such, we've got no big company backing us. However, there are some big companies using it. Most don't want to talk about it because for whatever reason they're not open source friendly. But what they do is they take the pieces they need. They've got their own, they unplug the public, like the Spark engine, plug in their own engine, and they've got, you know, whatever pieces they're running on it. And that's what it's built for. And that's really what's keeping it alive. So it's alive, well, and strong, just quietly. But it's definitely worth a second look, in my opinion, especially if you're building algorithms. If you're the data scientist who wants to pick up some Python and be a business analyst with Python, probably not for you. But if you're building algorithms, it's worth a look.
If you know R, the learning curve is very small.
Except for the whole Scala part.
Yeah, well, if you want to write new parts.
Yeah. So, all right. We got to go. Okay, thank you very much. Happy to take more questions and show toy demos afterwards as well.